Hello, my name is Brian Muzica and welcome to PCM Design Considerations for Space. So today we'll be talking about phase change material heat sinks and everything and anything you need to know to integrate them into your space system. So it is my privilege to introduce two extremely well-versed aerospace engineers here at ACT, Ryan, voicemail full Spangler. He's joining us with years of experience here at ACT and in the aerospace engineering, and he has done many of these phase change material heat sinks for spaceflight consideration qualification programs and testing programs. So he brings a lot of experience here, and I would urge everyone, please ask as many questions as you can, because we will be drilling both Ryan and Clayton at the end of this with your questions. So please ask questions as we go through everything. And the other speaker is Clayton Firehose, and we the name is actually very well versed because he is all about putting out fires. We tend to give him, myself and customers included, give him a lot of fires to put out, and he is a whiz at solving them very quickly and very adequately. So both two very well versed thermal engineers, and please ask as many questions as possible again. And with that, I'll give a quick overview of ACT just for those who are joining us for the first time, and then we will pass it over to Ryan and Clayton, who have recorded a nice segment giving everyone an overview on PCM, and then we will go into live Q&A at the end. So a quick background on advanced cooling technologies. We are a thermal management solutions provider here in Lancaster, Pennsylvania. We're a growing small business, over 240 employees and over 140,000 square feet here. We do the full gamut of thermal solutions, so everything from very low cryogenic temperatures to very high liquid metal temperature ranges, and all types of diverse applications. We'll be talking today about space type heat sinks. We also do military grade, highly reliable heat sinking and heat transfer devices, as well as industrial applications. So we have a lot of fielded and proven technologies, all focused on kind of high reliability and high performance thermal management solutions. You can see some of the examples we have there over to the left side of the screen. We do focus on kind of the highly innovative, cutting edge solutions. Our core values here are innovation, teamwork, and customer care. So we like to work very collaboratively and very closely with our customers to bring kind of newer technologies to the industries and go through the entire gambit. The space industry in specific, we're very well versed in understanding the design requirements, conceptually coming up with the adequate thermal solution, and then going through all the qualification acceptance testing regimens to make sure that it's space flight ready. So with that, I want to thank everyone for joining us today, and I will pass it on to Ryan and Clayton to give you kind of an insight into everything you need to know about PCM heat sinks. And once again, before doing that, please ask your questions, and we will be monitoring them live during the session, and we will be doing a live Q&A afterwards. And Ryan and Clayton are sitting next to me here. They're eager to get going, so please ask as many questions as possible. Thank you.
All right, so hi there. As Brian said, I'm Ryan Spangler. I'm going to walk you through the first portion of the presentation here. We're going to start off with some space considerations that are a little bit unique relative to typical terrestrial. But before we go on, I'd like to show a little bit of love to our MC for the day, Brian Muzica. Not only is he our sales and marketing manager, he's also an avid thermal enthusiast. And he has his BS in mechanical engineering. He's got a master's in business administration and engineering, but he's also got a PhD in life, and he's just one heck of a guy. So just want to give a moment to give credit to him. And I think with that, we're off. So in space, I guess the most obvious constraint or unique design criteria is that you don't have any sort of convection. The ultimate heat sink, you have to move all your energy to the radiator panels where it's dissipated into space via radiation. So that applies to, or operates under kind of the Stefan Boltzmann equation. The higher the temperature that you're operating your radiator panel at, the more effective or efficient they're going to be at dissipating that heat. I guess one consideration for the PCM then is because it operates between the sources that you're trying to cool and the radiator panel typically, it's going to actually operate at a lower temperature. So you want to be a high temperature for the PCM to enable a lot of dissipation to space, but you have to make sure you're below the max electronics temperature once all the delta T stack up is considered. So that requires you to have a lot of information regarding max component temperatures and the overall stack up back to the sink. Obviously, reliability is key. We can't send any sort of maintenance crews to space, and we'll touch on that a little bit more later. So you have to have a good understanding of your overall mission profile, which generally, if you're at this point, you have a pretty good idea of at least worst case, and you want to avoid any moving parts that are higher risk or tendency for failure. So again, just like any other application, whether you're flying terrestrially or you're out in orbit, you want to have low mass and volume so that you can stuff more of the important components in there to get more capability out of your system. So just a little bit of background on what exactly phase change material heat sinks are. They are a fully passive two-phase heat storage device, kind of like a thermal battery. So it generally operates with a paraffin wax, is the most common type within an enclosed system. And that has it's designed to have a phase change, either solid to liquid or liquid to solid, to absorb heat energy without allowing a significant temperature rise at the source or degradation at the source. The way it does that is it actually uses that latent heat as it goes through the phase change, which is orders of magnitude higher than the specific heat of a material. So we have an example there of water that has a specific heat of just over 4 kilojoules per kilogram degrees C, versus the latent heat is actually 2257 kilojoules per kilogram. So you get a significant amount of energy storage for a small volume of PCM. And that typically will occur at a set temperature, depending on the purity of the phase change material that you're using, whether it's a eutectic or it's some sort of a blend. That can occur at a point, or it can occur over a range. And in fact, some paraffin waxes actually have multiple phase changes where they'll go from solid to solid and then solid to liquid. So identifying where those phase changes are and how much energy is absorbed over that temperature is kind of critical for the design of the system. But the whole time that it's going through that phase change, it's somewhat preventing, I guess, a terrible temperature rise or fall if you're trying to prevent it from getting too cool at the source. So as I said, most common is paraffin wax for the temperature ranges that we see. There are also salt hydrides. They prevent certain challenges in that, being that it's a salt-based phase change material, it does have a tendency to be more corrosive, so material selection becomes much more important. And then you also have metals. Solders are technically phase change materials, and depending on the temperature that you want that phase change to occur and how much energy you want to store and any mass requirements, metals might actually be the ideal choice for you. It does come with a challenge in that at least the wax-based PCMs and the salt hydrides have a fairly low conductivity, even sub 1 watt per meter Kelvin. So getting the heat effectively into the PCM volume generally is the most critical or difficult task of the full system design. So there is some optimization between how much PCM you can have versus additional conductance or conductive elements into the wax, typically fins or either folded fins or machine fins. So you're iterating the thickness of those and the quantity or spacing of those versus how much PCM you have to determine what the appropriate choice is. So that's something we have a lot of experience in and are able to do fairly simply. One example here pops up on the top right, just showing you have your enclosure, which is in the red, typically machined out of aluminum, or it can be copper if absolutely necessary. Then you have the PCM. You can see that's got slits going through that because we have the folded film material that is protruding through the PCM volume to help conduct into that mass. So when do you want to use PCM heat sinks? There's a few different criteria that would fit the envelope or the mold for these types of systems. Generally, they need to be short, and that's relative speaking, short duration applications. So if you, let's say it's a fail-safe, and you need to keep something from over-temping for 30 minutes until you have the opportunity to shut off all your electronics, that might be a good opportunity to utilize like a phase change material system. Duty cycle operation, so if you're below 50% duty cycle, at or below 50% duty cycle, it may be a good technology to investigate because it's able to absorb the heat over that 50%, and then it has sufficient time to re-solidify for the remainder of that operational cycle. You have redundancy. I've already talked about the thermal runaway. There's also instances where, let's say, you're trying to dock to a system where you're trying to prevent the temperatures from falling too far before you're able to reheat the system. Another good use for these, can work in both directions. And then there's potential applications there for solder fatigue dampening. So in some systems, you're going to have fairly large temperature swings at the payload. So your electronics components that are soldered in place are seeing those, and the CT mismatches are causing some strain within your solder joints. This can help dampen the magnitude of those temperature swings. So there might be some application there. Then we do see instances where it could be useful for both CUBE small satellites, GEO or large satellites, and various scientific missions. I think I already talked to a number of those, and we're going to get into those in a little bit more detail here shortly. So just more of a reference for yourself there. So why would you use PCM heat sinks? Well, they're reliable and passive, and as we said before, Clayton has yet to get his license to be an astronaut repairman, and I certainly will not be going up because Heights and I do not agree. So you want it to be reliable and passive. This is a system that can enable a lot more capability out of your spacecraft by allowing you to use higher power amplifiers or just more powerful components than you would typically be able to use, because you'd be constrained by your radiator panel surface area and the amount of power that it can actually put out and reliably dissipate. So being reliable, passive, it's got no moving parts, and it's stable over thousands to tens of thousands of cycles. So those are two large benefits. And in general, again, you can get weight and volume benefits. So in instances where you do have the opportunity that you can size your radiator panels for peak load, putting a PCM volume in there to drastically reduce that for a duty cycle application can help reduce, obviously, the need to do that additional design, have those additional radiator panels, and end up cheaper, lighter, and occupying less volume, obviously. So again, there are certain orbit considerations. Depends on where you're actually going to be pulsing or where this needs to operate. Are you seeing sun? Are you eclipse? And that is something that we would take a look at in terms of a thermal design with an orbital profile, the worst case, hot and cold. Obviously, radiator panel size is dictated by the thermal load. We've already touched on that. So integrating that PCM can drastically reduce size of radiator panels needed because you can size it for actually time averaged dissipation rather than the peak load. So one example we'll get into in a little bit is if you have a 100-minute orbit, you got a 10-minute on period, and you're trying to dissipate 100 watts, your radiator panel goes from needing to dissipate that 100-watt pulse load to a time averaged approximate 10-watt load over the full orbit. And then heat source for survival. Again, if you have long duration cold states, one example might be docking to a system where you're disconnected from the electronics of the actual craft. can help prevent it from decaying to a worst case temperature. And there may be some applications there, as we allude to in the parentheses, for lunar night, surviving that. So I think we've told you the why and the when. I want to try and help define the process that we would go through, basically from you have an application that may need PCM. How do you identify that that's the best case solution for you? How do you go about designing it? And what steps do you need to take to get to testing? So I'll do a 30,000-foot view. I know Clayton's going to get into it in a bit more detail here shortly. So first, we would evaluate your application, right? As I said, figure out what requirements you have. Is it duty cycled? How much volume do you have? Can it be satisfied by simpler means, i.e. instead of using a PCM, is it something that just a little block of aluminum can take care of? So we do a quick feasibility study using your boundary conditions just to determine PCM might be a high fidelity candidate for that application. And then we look at the source to the sink, just make sure we have the temperature swing available. If possible, we'd say, you don't have enough temperature rise from your radiator panel to the source to make this reasonable. So that's step one. Then we go into the design once we figure out, yeah, PCM's a potential candidate here. So we look at, all right, what's your overall temperature range? What is the temperature you're trying to keep your components to? And that'll help derive the PCM selection, that plus how many cycles you need to survive. So we figure out, all right, we have this PCM. What size do you need? How much PCM do you need? Where can that PCM go? Sometimes you're very volume constrained at the source. You want to move that heat from the source to the PCM module, which resides somewhere else. So that's something we'd take a look at and figure out, if that is the case, how do you route the heat flow from the source to the PCM reservoir? So beyond that, we get into some more of the analyses. So we do a heat sink conduction analysis. So just looking at, first we do a baseline, see what your overall temperature rise is, and then we do some optimizations, delta T from the source into the PCM by varying the fin spacing and thickness until we get what we feel is an appropriate delta T into the system that's able to meet your requirements. If required, and we'll get into this shortly, we do any additional heat pipe analysis, say you need heat help spreading or transporting the heat. So we do that kind of in parallel with the heat sink conduction analysis. We take those two things, combine them into an operational thermal analysis, which is, it can be a steady state, depending on your application. If it's just a fail-safe, as we talked about, it needs to work one time, and we know how long that is and how much the losses are. Or we could look into more of a transient, orbital thermal analysis and run it for several orbits until we see what the true repeatable response of the system is, and make sure we don't have any sort of thermal runaway. And beyond that, since these will be operating in a vacuum environment, we probably look at some level of structural analysis, typically pressure analysis to 4x me up, but that's a little bit more for later. Beyond that, we have something designed, we're building it. We would want to obviously validate the performance, do a transient thermal test as reasonably similar to the application as we can, do the various pressure and leak tests to verify the hermeticity and that it is a sufficient pressure vessel. We have the thermal cycling just to show that it freezes, thaws, and retains, I guess, its properties through those cycles. And PCM validation, which is something that we've done before, just to verify that over thousands or tens of thousands of cycles, the material is stable and you get a repeatable latent heat storage out of them. So just to walk it through in a bit more typical fashion. So here we have just an example. You have a heat load. It wants to put out 100 watts for 10 minutes. Call back to earlier because I knew this was coming. You have a certain amount of area, 4 by 4 inches area that's being applied. You are not constrained in the Z direction, so it can be as thick or thin as it needs to be. And you're starting, worst case, at 40 degrees C. So the hottest that it's going to start pulsing is at 40 degrees C. You want to maintain 55 degrees C at the interface. So that's important to note. The max temperature and the starting temperature are the temperatures the PCM vessel sees, particularly where the source interfaces. So first thing that you can do if you're not entirely sure, is PCM going to be a good fit? Is this reasonable? We offer a free to use PCM calculator. The link's up there. You can also go to our website. I believe in the resources, there's a calculator section there where you can find this. So we just populate. This is pretty much exactly the little table that'll pop up. You want to populate this information, the initial temperature, final temperature, which we derive from the example, the amount of power it needs to store, the time, 10 minutes. Obviously, make sure your units align, because I think that defaults to hours, and then your base width and base length. And rather than a simple, just latent heat check, it'll print out something that looks like this. It'll run those calculations for 3 different PCMs, show you the approximate base plate temperature, which is shown on the graph there. On the right, you'll see the various parameters for the options, how much volume approximately you need, what the approximate mass of the system becomes, how much of that energy is stored in the latent heat. So it does take into consideration specific heat, which a lot of just typical hand calculations won't do for you. So once you run this plot, if it looks feasible, you want to take some next steps. At the top there, above the plot, it actually has this opportunity where you can, I believe, print out the PDF of it and submit it even to ACT, and then we can be in contact to talk more nuances about the design. Beyond that, again, that's looking at a very simple box, assuming that heat load is uniformly distributed. Most times that's a pipe dream, right? So you'll either have discrete loads, or you can't put your source directly at the sink. So in some cases, for the discrete heat loads, let's say you have that 4-inch by 4-inch box, but your heat load is a 1/2-inch by 1/2-inch square right in the center. So you're going to have either a very thick PCM module where most of that 4x4 area is not being utilized, and then you'll have a tremendous delta T through it, or you need something to help you conduct in plane before it gets to the PCM to help maintain a low or reasonable delta T. In which case, one option that you have is utilizing heat pipes for spreading in plane there before it gets into the PCM. Those heat pipes, since they're in front of the PCM and the resistance network, are going to have to see and move that full 100 watt of power. The other application, let's say you do have your PCM at the source, but it's a good distance away from the sink. You can use either CCHP or copper water heat pipe to take that heat from the PCM to the radiator panel and even spread it in plane to get a nice efficient dissipation out of the panel. In that case, you'd see time average power. So calling back again to the verbal math that I did earlier and the example we just touched on, 100 watts over 10 minutes, you got a 100-minute orbit, which is a 10% duty cycle. Assuming you're also dissipating as it's storing, that results in about 10 watts for the heat pipe to transport. So a significant reduction, obviously, in what the heat pipe and thus the radiator panel see. So I talked to them a little bit. There's a couple options that are typical to be used for those. The first is kind of the old workhorse for these systems. The aluminum ammonia CCHP is something we have, I think, over 50 million on-orbit hours without failure for currently. They're very good at transporting a lot of energy, very long distances. There is some limitations in terms of the ground testing. They have what's referred to as an axially grooved extrusion. So it's able to move a lot of power whenever there's not a gravity head. It's just not able to wick well against gravity or pull liquid back up to an evaporator. So there's a certain constraint that will put on your integration and testing side of things. And you are somewhat limited in the heat fluxes. Generally, once you get to the bus or radiator panel side of things, it's reasonable, and that's where these typically see a lot of use. But if you're directly at the source, they're generally in like a max of 5 to 10 watts per centimeter squared, which can be inhibitive. The other option, which I talked to, was the copper water heat pipe, something that we do have spaceflight heritage with as well, and are seeing operation currently. They don't have quite the distance to travel. However, they do afford you the opportunity to, in some cases, test on ground in any orientation. And they're generally good for the temperature ranges your electronics components are going to work in, and significantly higher heat flux. They're able to receive that relative to the CCHPs. So where the CCHPs were 5 to 10 watts per centimeter squared, these can go up to about 50 watts per centimeter squared. So again, the question becomes, all right, you know you have a PCM module, you know it can store the amount of heat, you know you have a discrete heat load and you need to spread that. What's your next steps? Well, we offer also a heat pipe design calculator on the website, similar location, resources, you go to the calculators. It's very specific to copper water heat pipes. If you're interested in using CCHPs, you can contact us, and we have a catalog that we can look to provide that'll help define the transport limits of those systems. So in this example, I'm just assuming you have an approximate heat pipe length. Let's say your source is here, your radiator panel's here, you want to spread in plane. So I'm saying it's about a 10-inch long heat pipe. 4 inches of that's contacting the PCM heatsink. The other 4 is on the radiator panel. I'm looking at 2 cases here, and this is imperative to not just think about the on-orbit application, but if you do have to test on ground, you want to capture your worst case against gravity. So on the left is microgravity. You'll put 0 inches against gravity, horizontal type application. And on the right is your worst case operation, which in this case I just calculated is about 6 inches. So first we'll take a look at what that calculator will provide. This is just an example of all heat pipe limits less than or equal to 1/4 inch. So it runs one internal wick structure for, looks like 6 different diameters of heat pipe. And if you just look at this for the on-orbit operation or the horizontal operation, you'd say to yourself, well, I can use any of these heat pipes, right? Because how this curve works is, that operating point, the star, needs to reside underneath the limits. The limit is showing the max amount of capillary or power that it can carry. And right now, your star is sitting below every single one of those curves. So if you design for the orbit configuration, maybe you'd end up with, an 1/8 inch or even a 3 millimeter diameter heat pipe. However, once you populate it with the worst case orientation, you can see the gravity head plays a significant role on how much margin you have over that requirement. So now you're just barely under the 4 millimeter curve. So had you designed for the 3 millimeter diameter heat pipe, you'd be having some problems. So at this point, I'm going to kick it over to Clayton, and he'll continue carrying us through the slides here.
Thanks, Ryan. Yeah, so I'll continue where Ryan left off there in our process flow. Basically covered the feasibility study and the initial evaluation of the application. So I'll get into some of those later tasks. So the first one up here then next would be design. Designing the PCM heatsink. The first step there typically is to determine our phase change material. So a very key point that Ryan mentioned earlier is the desired melt temperature. Typically going to be a little bit of margin below your max allowable temperature of your source. So again, there's many options out there, pure paraffins, as well as some commercial blends and proprietary versions that other manufacturers do also have. And also, while looking at that melt temperature, also important to continue taking a look at the energy storage or the latent heat. Some of the various PCMs or slight changes of paraffins have somewhat substantial changes in latent heat, as well as density. So again, going to be keeping a close eye on that while doing that evaluation and selection of the phase change material. The next step then, determine if the PCM is a mass volume win. Again, going back and balancing radiator size and mass versus the PCM size and mass. If your design is already radiator size limited and you need a solution such as PCM, definitely something you need to consider at this point in the design. Continuing on then to locating the PCM, again, Ryan alluded to this a little bit earlier, understanding geometric constraints, whether you can directly attach the PCM heatsink or the source heat input devices to the heatsink, or if we need to locate it at the radiator panel or some location in between where we have the space and volume constraints to store that heatsink. And then lastly, transport heat as needed. Again, going back to what Ryan was mentioning, and using our combining technologies, heat pipes, CCHPs, or copper water heat pipes to move that heat where we need it to the PCM heat sinks. So then after the design, kind of establishing those details and those parameters for the design, we'll go into the analysis of the heat sink. First up being structure/conduction path thermal analysis, looking at that metal housing that's going to store the PCM and analyzing that conduction path because our paraffins, our typical phase change materials are low thermal conductivity. We need enhancements to get that heat to the PCM and melt the PCM in a more uniform fashion. What we typically see are metal fins and metallic housings, but there are other options out there, such as aluminum foams. Ryan alluded to folded fins. We can also machine fins into the sink as well. Again, the thermal design and storage is really going to dictate what we can and can't use for the fin materials or geometry. And then also conductivity enhancements, whether it's through holes or bores through that PCM heatsink to transport the heat to the location where we need it. Again, a very thick PCM heatsink may need those through plane heat pipes for the conductivity enhancement. Next up then would be a more detailed heat pipe analysis. Ryan already alluded to our online calculator. That'll get you in the ballpark, but we do have in-house software to refine and further analyze the heat pipes, confirm that they will be able to transport the heat, and we're getting the uniform spreading that we're looking for. Next up then, operational thermal analyses. Basically, first off would be a quarter model or full size model of our thermal solution, the heat sinks with the heat pipes integrated, melt and freeze, seeing just a melt temperature curve here currently, but also very critical to analyze that refreeze as well to ensure that we can come back to the solid state before we get into the next cycle, take advantage of the full energy storage. So then that also leads into the orbital thermal analyses as well. As I alluded to, we don't want what's occurring here in the image to the right, where we're getting a thermal runaway because we are not in an off state long enough to completely refreeze all of the PCM. Now, for these analyses, we'll typically simplify the heat sinks as bulk thermal conductivities, just because our models do get large and running these orbital analyses are very computationally intensive. So continuing on with analyses we will typically perform, Pressure analysis, again, Ryan alluded to this a little bit earlier. The heat sinks are sealed vessels. They are pressure vessels. So doing that detailed analysis to ensure we can sustain any expected operating pressure. Again, that pressure is dictated by voids and density changes within the PCM heatsink. Again, we have extensive experience designing these heatsinks and are comfortable with our sealing techniques and understanding of the process. And again, a typical design will be designed to 4x MEOP. Pressure analysis results, again, just validating that we're not going to exceed that yield on the housing material in any location. Analysis that we'll run are vibration analysis. Typically, we stick with modal analyses when we're performing the PCM heatsink design. They are massive because of the weight of the phase change materials. And typically, we kind of push further structural dynamic analyses for higher level assemblies. But again, we'll typically see a modal analysis just to see what kind of fundamental natural frequencies we're getting out of our heatsink. And again, there's just a quick example or representation of a PCM heatsink with transport heat pipes. We have the PCM heatsinks there to the left and the radiator panel there to the right with the linking and spreading CCHPs attached. And then the final analysis, these aren't as common as the other two, but sometimes customer would like to use the heatsink as some kind of structural component. So just applying static loads and validating the heatsink can handle those loads. There are some geometric constraints or variables, knobs that we can turn to stiffen up or handle those additional stresses. The last step here that Ryan had gone through is the validation of the sink. And again, just running it through our expected operation, applying the power with representative sources, multiple thermocouples across the heatsink to validate any spreading. And here, the picture to the right, you can see that rapid ramp up as we're taking advantage of the specific heat, the flattening or plateauing as the PCM is melting with the latent heat. And then as the PCM completely melts, we get back into that same specific heat slope ramp up. And then here you can see the power was turned off in this test, ramp down again at that specific heat, plateau, flat line as the PCM is freezing, absorbing that energy, and then again back to the constant ramp rate down as it takes advantage of the specific heat again. So the next very common test that we run are proof pressure / leak tests. Basically there we're going to take the heatsink up to its expected operating temperature and pressure, again based on voids and the expansion or changing density of the PCM. Run it through that elevated temperature, hold it there, orient it with our sealing mechanism down with respect to gravity to see if anything leaks out. Also visually inspect around any kind of braze joint or gasketed joint along those seams, and again validating the pressure containment capabilities. Another option that we do see occasionally are instrumentation such as strain gauges, again just to validate those stress analysis that we previously ran. Very common test is the thermal cycling, just running the PCM heatsink through numerous cycles, whether it's full life or any expected factor of safety on that can be run in an environmental chamber or with specific heat inputs applied as it was designed to handle. Intensive to run more of a simulated load rather than an environmental chamber, so something to consider when specifying any kind of validation requirement. The last point here is PCM validation. That would basically be taking samples of the PCM that we've previously selected and running validations of melt temperature, latent heat, as well as any kind of life limits or changes as cycles are accumulated on the phase change material. The image here you can see is our in-house DSC, differential scanning calorimetry device. Again, basically taking a small sample and running it through basically the profile you see to the right, heating and cooling that sample and measuring heat input required to melt and freeze the sample. And we do have experience running these validations in the DSC and then applying tens of thousands up to 25,000 cycles on the sample and measuring again these latent heats and melt temperatures throughout the life to validate the phase change materials that are capable of handling those very large numbers of cycles without degrading. All right, so that basically ran us through the remainder of our process or flow for the PCM heatsink design development. So next up here is just a case study of a PCM heatsink design. So again, the initial state or conditions that we may typically receive would be a power greater than 300 watts, a duty cycle of less than 15%, and a radiator panel size restriction levied on the design. So right off the bat, this is looking like a PCM solution. We've got high power that's only on for a very relatively short duration, and also restricted radiator panel size such that we cannot design to meet full load heat rejection. So again, determine if the PCM is the best solution. Insufficient thermal mass to maintain the temperatures. PCM could reduce the radiator size by an order of magnitude to meet these requirements. So we've identified that PCM is a very good candidate for this. So then we'll look at locating the PCM. In this case, you can see the picture to the bottom there. We've actually got our components on the PCBs. Locate the PCM mass between the source and our thermal links or CCHPs that will run to the radiator panel. So a good location. One thing to consider here is the PCM heatsink is already fairly well optimized for our thermal resistance through in order to get the heat into the PCM. It will also be a fairly good conductor to go straight through into the thermal links as well. And again, kind of going back to the bullet points there, get the heat to the radiator panels with the thermal links. We've got our constant conductance heat pipes, aluminum ammonia, and moving those to the radiator panels, as well as CCHPs on the radiator panel to help spread and dissipate the heat. So then some results on that analysis of the radiator panel size reduction. You can see here the picture to the left. Basically required radiator size or sink temperature. Again, this one is showing without our PCM, looking at 4,000 square centimeters to achieve continuous heat rejection. go ahead and analyze it with the PCM. And the scales are a little misleading on here. So the numbers are really what's key to look at, and a significant order of magnitude reduction in required radiator panel size once we implement the phase change material in this specific design. So that's everything that I had. So we'll switch back over to Ryan, and he'll give us a brief summary of what we went over today.
Obviously, and this comes as no surprise to anybody, spacecraft, satellite, probe, thermal design that's unique relative to anything that you'd see, here terrestrially, not only in terms of temperature ranges, but also the reliability that's needed to assure that you're not going to launch a tens of millions to even more dollar value asset into space and have something as small as an heat sink bring it down or cause it to fail. So that plus the vacuum environment actually turns these PCM modules into a pressure chamber, and Clayton walked us through some of the ways that we take a look at that and just validate not only can it handle the pressure, it's not going to be leaking PCM and causing it to deposit on your various components within the system. We are happy to help you along in your design, take a look at some of the things you have. As of right now, that's pretty much all that we had planned for the webinar itself. Now we will take you back live to the literal roundtable discussion with Clayton and myself.
Right. Okay. Well, again, thanks everyone for joining, and thanks for the questions. We have had several coming in here. So we got Ryan and Clayton here. Let's go ahead and get started. The first one, which I don't think is actually a question, but more of a comment. I think it's one of our customers wrote in that Ryan's voicemail is not actually always full. And he also commented that the best time to reach him is after 8 p.m. Eastern time. So we appreciate that comment, and we'll definitely pass it along.
And so
yeah, the first question, just kind of a general question, is, and not necessarily related to PCM, but what's the most interesting project you've worked on at ACT?
So for me, well, there was one for I think the DART program, which is it's marketed as the first planetary defense mission or whatever. We provided some thermal control hardware for a small satellite. The sole purpose was to kind of project through space and ram into an asteroid, and they wanted to see if they could influence its trajectory, which is pretty cool and also somewhat doomsday-esque. That's probably mine.
Clayton?
Yeah, I guess my answer would be kind of a long-standing project in which we kind of adopted or adapted our standard copper wire heat pipes to perform in space and survive the harsh environment of space, developing space copper pipes. A long, arduous task, but very, very successful and very rewarding.
Excellent. The next question, we'll go to Clayton for this one, is the PCM choice mainly a function of the working temperature?
It is largely a function of your working temperature. Again, kind of selecting a PCM melt temperature that is right below or above your critical component temperature that you're trying to survive. Again, you could, if you have a large difference between your starting point and that critical temperature, you can kind of select anywhere in between there, but that is a critical part. There are some other things that you would be looking at, such as that latent heat of fusion and the density, and making some minor trades there, but primarily you are going to be looking at that.
Yeah, very good, very good. The next question will go to Ryan, and there's two kind of similar questions also related on temperature here. The first one is can you pick any phase change temperature, melt temperature? And the second one is that you mentioned that there's a range associated with the melt temperatures during the presentation. And the question is, how precisely can you predict the melt temperature of various PCMs?
All right. Good questions. I'll see if I can do them justice. So the first is there are a wide variety of different types of PCMs that you can select, and they kind of envelope different temperature ranges. So very cold, sub-zero, you can get some, what are they, the salt hydrate kind of phase change materials. More typical operating temperatures of electronics are kind of in a paraffin wax kind of range. And if you get really hot, you can go into actual metals, solders, etc., phase change materials. Each one kind of poses different challenges. Paraffins generally are the least corrosive, easiest to work with. They don't expand as they, have well-defined parameters in terms of density for solid, density of liquid. The salt hydrates are corrosive, and a lot are actually water-based, so they will expand whenever you want them to contract. So that's one nuance, and it eats away typical used. And the second was how precisely can you control that temperature? So we do, as Clayton had presented on in the presentation, have the capability to test with our DSC or other means the precise point or range at which it's melting. We can feed that into our thermal models of the system, and we can play with the resistance from the interface into the PCM to get your surface temperature that you're mounting to very, very close to what you want that surface to be at.
Excellent, thank you. Next question, Clayton, will go to you. For a PCM heatsink, what is the ratio of PCM mass versus the entire mass of the heatsink?
Sure. I guess typically we like to give the generic answer of it being about 50% by volume. Pretty quick and easy to determine what that is with the mass. But again, with the paraffins being a kind of a workhorse when it comes to PCMs, again, aluminum housing, they're kind of our workhorse as well for those. You can kind of do some rough calculations on that there. But generally speaking, it's about 50% by volume.
Very good, very good. Okay, the next question, and this looks to have some a very detailed or specific, so there might be an application behind this one, but to Ryan, have you ever worked with or delivered PCM materials that can sustain about 15 degrees surface temperature?
Yes. Yep, we have worked with around that temperature range. Fortunately, you're still in kind of the paraffin wax type of range, so you don't have to work with those salt hydrates that are highly corrosive. And there's a few different materials that kind of envelope that temperature. So yeah, we can influence the thickness of materials and contact resistances to yield a roughly 15 degrees C surface temperature.
Very good, very good. And the last question we have, and we'll wrap up here before 3 o'clock Eastern, we'll go to Clayton. Can you comment on the manufacturing process of the structure?
Absolutely. We're seeing kind of two primary means of making the structures, specifically to aluminum. I'm going to speak to here, I guess. First would be kind of more widely adopted or used in the applications that we see, and that's basically a vacuum brazed aluminum housing. Again, whether that's a machine base with a pocket and putting folded fins in, or some kind of aluminum foam, or machining fins right in that base and then having a aluminum lid that you're going to vacuum braze onto that base. The other side of things, when it comes to maybe rapid prototypes or trying to get a validation model rapidly, is 3D printed is also an option. We have built several PCM heat sinks that actually use 3D printed aluminum, and they perform very well as we would expect.
Okay, and just to add on to that, is there any design consideration differences between the two manufacturing options?
Certainly a lot more to think about when you're 3D printing. Just like any other 3D printed part, you've got the loose powder that you have to create holes to evacuate that powder out. There's some thinning areas, maintaining proper wall thickness and things like that. Also kind of makes 3D printing a little challenging, but there's also challenges with vacuum brazing as well. And over the years, we've been developing our knowledge and expertise in that vacuum brazing and working with key suppliers that we work with every day to design with those considerations in mind.
Yeah, so certainly a lot of trades, no matter very early on in the process between both and also PCM selection, I'm sure.
Absolutely. Yeah.
All right, well, very good. Appreciate everyone joining us today. If we didn't get to your question, because I think there's still a couple coming in, we will certainly respond to them afterwards. And I want to, again, thank our speakers, Ryan and Clayton, for giving us a very well-versed topic. And again, please continue to communicate with us, ask us questions. We'll definitely respond to you afterwards. And thank you all for joining us. Have a great day. Clayton, nice shirt.